Hi, Assalamualaikum. My name is Ellyana. So this is the video of assignment 2 for group 7. The first task of the assignment is to derive the second order ordinary differential equation of the coilover. So step 1 is the introduction to the coilover system. A coilover suspension consists of two main components, a coil spring and also a hydraulic damper. And for this analysis, the following assumptions are made. The motion is one-dimensional, the spring obeys Hooke's law, the damping force is proportional to the velocity, the spring is initially at its equilibrium length, the weight of the automobile is neglected, and the last one is an external force may act on the suspension. The second step is we will identify all forces acting on the mass. There are three forces act on the mass. The first one is spring force. So according to Hooke's law, F is equal to negative Ky, where K is the spring constant, Y is the displacement from equilibrium. The second force is the damping force. The damping force is proportional to the velocity, where F is equal to negative L dy over dt, and L is more than 0 is the damping coefficient. And the last force is external force, where F is equal to F in terms of t, and F in terms of t is a time-dependent external force. Now we will apply Newton's second law to the three forces just now, and by substituting each force, we will get m second derivative of y equal to negative Ky, negative L, first derivative of y plus external force Ft. In step 4, we will obtain the general equation of motion by rearranging the equation that gives this equation. So this equation is called the force-damped vibration equation because the system is subjected to an external force. In step 5, we will convert the previous equation to free vibration, which is the external force is equal to 0. So we will get the general equation like this, and this is called the free-damped vibration equation. Next, we will normalize the equation by dividing each term by m, and we also define omega square is equal to k over m and 2b is equal to L over m, where omega is natural angular frequency and b is more than 0 is the damping constant. By substituting this definition, we will get the standard second order differential equation for a damped spring mass system. In step 7, we will assume a trial solution where y is equal to exponential rt and find the first and second derivative, and then substitute into the differential equation and factor out exponential rt. And since exponential rt is not equal to 0, we will divide both sides by exponential rt and giving the characteristic equation like this. In step 8, we will solve the quadratic formula, and by simplifying it, we will get r is equal to negative b plus minus square root of b square minus omega square. So the type of solution depends entirely on the discriminant under the square root, which is b square minus omega square. There are 4 types of solution that we will look after this. For case 1, under damped motion, when b square minus omega square is less than 0, the roots are complex. So we will obtain the general solution for under damped motion as shown in the last row. Next, for case 2, critically damped motion, when b square minus omega square is equal to 0, there is one repeated root, r is equal to negative b. So the solution is as shown in the last row. Next, for case 3 over damped motion, it is when b square minus omega square is more than 0, there will be two distinct real roots, r1 and r2. Therefore, the solution for the overdamped motion is as shown in the last row. And the last case is undamped motion. It is if the damper is removed, the L is equal to 0 and then B is equal to 0. So the governing equation will become the second derivative of y plus omega square y is equal to 0. So the solution is like this for the undamped motion.
Estimation of displacement versus time graph for the undamped, underdamped, overdamped, and critically damped conditions. We will use the following irrational constants. Let's look at case. The general solution minus y equals to 1 we apply t equal to 0 in y, we will get 8.2 times then we differentiate and get y prime equal to negative c1 sin omega t plus c2 omega cos plus omega t. Then we apply t equal to 0 in the first derivative, we will get c2 equal to 0, and the final general solution for undamped condition will be equal to y equal to 8.257 10 times to the negative 2 cos 3.591 t. We add the solution for undamped conditions in Desmos to get the graph of undamped motions. Next, for the case 2, underdamped conditions, the general solution for underdamped is y equal to exponent to the power of negative bt multiplied by c1 cos of the square root of omega square minus bt plus c2 sin of the square root of omega square minus bt. We will get L equal to 8.937 times 10 to the 0, b equal to 1.66, and omega equal to 3 g. When we apply t equal to 0 in y, we will get c1 equal to 8.257 times 10 to the negative 2. Then we differentiate and get y prime equal to negative 1.566 exponent negative 1.566 t, c1 cos plus c2 sin plus exponent negative 1.566 t negative c1 omega sin plus c2 omega cos. Then we apply t equal to 0 in the first derivative. We will get c2 equal to 3.999 times 10 to the negative 2. Final solution for the underdamped condition will be y equal to exponent negative 1.566 t multiplied by 8.257 times 10 to the negative 2 cos 3.233 t plus 3.99 times 10 to the negative 2 sin 3.233 t. Finally, we enter the final general solution for underdamped conditions in Desmos to get the graph of underdamped motion.
Moving on, case 3 critical damping condition, the general equation is y equal to C1 plus C2t exponent negative pt. I we will get 20.49, b we will get 3.591. So apply y0 at t equal to 0, we will get C1 equal to 8.257 multiply 10 of negative 2. After that, we differentiate y and we will get y prime equal to C2 exponent negative pt minus b C1 plus C2t exponent negative pt. At t equal to 0, y prime equal 0, C2 will get C2 equal to 2.966 multiply 10 of the power negative 1. Substitute the value in y, we will get y equal to 8.257 multiply 10 power of negative 2 plus 2.966 multiply 10 power of negative 1t exponent negative 3.591t. We enter the final general solution for critical damping condition in Desmos to get the graph of critical damping motion. Lastly, for case 4 overdamp condition, the general solution for overdamp is y equal to C1 exponent power of R1t plus C2 exponent power of R2t. Then I equal to 2.684 multiply 10 power of 1 and b equal to 4.702. Since we have two distinct aerial roots, R1 equal to negative 1.723 and R2 equal to negative 7.681. When we apply t equal to 0 in y, we will get C1 plus C2 equal to 8.257 multiply 10 power of negative 2. Then we differentiate and get y prime equal to R1 C1 exponent power of R1t plus R2 C2 exponent power of R2t. Apply t equal to 0 in the first derivative, we will get C1 equal to 1.020 multiply 10 power of negative 1 and C2 equal to negative 1.943 multiply 10 power of negative 2. The final general solution is y equal to 1.020 multiply by 10 power of negative 1 exponent negative 1.723t minus 1.943 multiply 10 power of negative 2 exponent power of negative 7.681t. We enter the final general solution for overdamp condition in Desmos to get the graph of overdamp motion. These are how they looks like when all the four conditions, undamp the purple color, underdamp the red color, critically damping the green color and overdamp the blue color in one graph.
For case 1 emissions, the undamp graph show a continuous sinusoidal oscillation with a constant amplitude because there is no damping force to dissipate mechanical energy. As a result, the system oscillates indefinitely and never reaches equilibrium. Although this behavior is useful for theoretical analysis, it is unrealistic for the actual vehicle suspensions. In underdamp motion, the underdamp graph show oscillatory motion with an exponentially decreasing amplitude. The spring continuously exchange potential and kinetic energy, while damper gradually remove energy from the system. Consequently, the oscillations become smaller over time until the system settles at the equilibrium position. This behavior provides an excellent balance between ride comfort and vehicle stability, making it the preferred operating condition for the most automobile suspension system.
For case 3 critically damped motion, the critically damped graph shows that the displacement returns to equilibrium without oscillating. Among all non-oscillatory responses, this condition achieves equilibrium in the shortest possible time. It prevents overshooting while ensuring a rapid response, making it desirable for system requiring a fast stabilization. Discussion. For case 4 overdamp motion, the overdamp graph also shows no oscillation. However, because the damping force is greater than the critical value, the suspension returns to equilibrium much more slowly. Although vibrations are eliminated, the slow response reduces the suspension's ability to recover quickly from a successive road displacement, resulting in a less responsive and less comfortable ride.
The conclusion for this video is the simulation results show that the undamped system oscillates continuously, the underdamped system exhibits gradually decreasing oscillation, the critically damped system returns to equilibrium in the shortest time without oscillating, and the overdamped system returns to equilibrium slowly without oscillation. Among these, the underdamped condition provides the most suitable performance for automobile suspension by balancing ride comfort and vehicle stability. That's all for this video from Group 7. Thank you!